Hello everyone, I am Dr. Shubhra Mishra from the Department of Physics. In today's lecture, we are going to discuss the topic of electric field and electrostatics as part of our course on fundamentals of engineering physics. In this lecture, we will start by discussing the nature of electric charges and Coulomb's law, which describe the force between charges. We will then introduce the concepts of the electric field, electric flux, electric dipole, explaining how it helps us visualize and calculate the influence of charges. Finally, we will explore into electrostatic potential, important concepts for understanding the energy aspects of electric fields and how this relate to real world applications. First of all, what is electrostatic? Electrostatic is the branch of physics that deals with the study of electric charges at rest. It focuses on the forces, fields and potential that arise from static electric charges as well as the interaction between charge object when they are not in motion. Unlike current electricity, which involve moving charges, electrostatic focuses on stationary or slowly moving charges. Imagine the force between your hair and a balloon after you rub it. Yes, that's electrostatics in action. What is moving and non-moving charges? Moving charges means to electric charges in motion, typically in form of an electric current. The movement of charges through a conductor is the basis of electricity, and non-moving charges means static charges. Actually, they are electric charges, they remain stationary. It means in rest. They accumulate on the surface of an object and do not flow. Actually, electrostatic topic is a cornerstone of electromagnetism. It helping us understand the forces, interaction between the charged particles. We will explore essential concepts such as electric charges, electric field, and let us start with electric charges. What is electric charges? It is a fundamental property of matter. Electric charges comes in two types, positive and negative. Positive charge occurs when there are more proton than electron, like in a proton. On the other side, negative charge happens when there are more electrons than protons, like in an electron. What is positive charge? Positive charge means repels other positive charge but attract negative charges, and negative charge repels other negative charge but attract positive charges. These properties allow objects to exert forces on one another, and it is quantified in coulombs. For instance, a single electron carries a charge of approximately 1.6 into 10 to the power minus 19 coulomb. Now, we are going to explore the conductors and insulator. What is conductor? What is insulator? These are materials that play a crucial role in our everyday life, especially when it comes to electricity. What is conductor? What happens when you turn on a light switch? Yes, electricity flows and the light turns on. The material inside the wire that allow electricity to flow easily is called a conductor. Conductors are material that allow electric charges to flow through them easily. The best conductor is what? The best conductor are metals. Then we discuss about insulators. What do you think an insulator does? An insulator is the opposite of a conductor. It is a material that does not allow electric charges to flow through it easily. Insulators are used to protect us from the electric shocks and to keep electricity where it should be. For example, the plastic coating around electrical wires prevents us from getting shocked when we touch the wires. That is because plastic is an insulator. Now, we will discuss properties of electric charge. For example, two opposite charge will push away from each other, while a positive and negative charge will push towards each other. First, we are going to explore properties of electric charges. First is quantization of charges, means charges comes in fixed amounts like little packets. The smallest packet is called the elementary charge. So, charges are always a whole number of these packets, never in fraction. So, charges exist in discrete amount multiples of the elementary charges. Next is conservation. This is like a magical rule of nature. It means that the total amount of charge is in closed system like in a seal box, stays the same. Charges can't just disappear or pop out of nowhere. They can only move around. So, if one part gains some charge, another part must lose the same amount. Keeping the total constant means the total charge is an isolated system remains constant. Next property is additivity. If you have different charges in a system, you just add them up to find the total. It is like adding and subtracting numbers. For example, if you have plus 3 units of charge and minus 1 unit of charge, then the total net charge is plus 2 units, because plus 3 minus 1 equals to 2. The net charge is the algebraic sum of individual charges. Now, we talk about the last point, interaction. How charges can move from one place to another. This is known as actually charge transfer. There are two main ways it can happen. First is conduction and second one is induction. Let us discuss conduction. What is conduction? Imagine you have a charged object like a balloon that's been rubbed on your hair. If you touch it to a neutral object like a metal spoon, some of the charge can move to the spoon. This happens because the spoon allows charges to flow through it. It is like pouring water from one cup to another. The charges flow directly from the balloon to the spoon, making the spoon charge. Let's we talk about the induction. What is induction? It happens without any direct contact. Imagine you bring a charged object like a negatively charged balloon and close to a neutral object like a metal cane. The charges in the cane get rearranged. Positive charges are attracted towards the balloon and negative charges are repelled to the far side. If you then touch the cane with your hand, some charges can flow away, leaving the cane with a net positive charge even though the balloon never touched it. So, interaction means attraction or repulsion. It is the fun part. Charges love to interact with each other. Here the simple rule, like charges repel and opposite charges attract. So, if you have two positive charges or two negative charges, they will push away from each other, But if you have one positive and one negative charge, they will pull towards each other. It is like magnet with opposite poles, means like charges repel and opposite charges attract. Our next topic is electric field. What is electric field? Electric field is a vector field that represents the force per unit charge exerted on a small test charge placed in the field. It provides a way to visualize how charges influence the space around them. The strength and direction of the electric field are given by the equation E equals to F by Q. What is E? E is the electric field, F is the force and Q is the charge. Next, a very important concept in our electrostatic topic is Coulomb's law. What is Coulomb's law? Coulomb's law quantify the force between 2 point charges. The force is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. And here F equals to K Q1 into Q2 by R square. This formula help us calculate the magnitude of the electrostatic force and understand how distance and charge magnitude affect the interaction. Then we discuss Coulomb's law in vector form. Here diagram shows two charges. Suppose we consider one charge is Q1 and second one is Q2 at the point A and B in vacuum. The distance between two charges is small r. As charges are like, we know that they repel each other. Suppose F21 is the force extracted on charge Q2 by charge Q1 and F21 is the force. Similarly, for F12, F12 is the also charge. So, this equation shows the Coulomb's vector form. Next, we are going to explore the concepts of electric field. Electric field is a fundamental idea in physics that help us understand how charges interact with each other even from a distance. An electric field is a region around a charged object where other charged objects experience a force. It is a way of describing the influence a charge has on its surroundings. Here the diagram represents the electric field with arrow pointing outwards. The direction of the electric field is defined as the direction in which a positive test charge would move if placed in the field. For a positive charge, the field points away from the charge, while for a negative charge, it points toward the charge. Electric fields are everywhere in our daily lives and in many technologies. First, electric field store energy in capacitor, which are used in electronics to regulate power supply and store energy. Electric field are fundamental in functioning of transistor, diode and other components in electronic circuit. Devices like electrocardiograms ECG use electric field to monitor the heart activity. Electric field are crucial in particle accelerators and other experimental setups. Let us discuss the electric field generated by a short electric dipole. A short electric dipole refers to a dipole where the separation between the charges is much smaller than the distance from the dipole to the point where the field is being calculated. An electric dipole consists of two equal and opposite charges, suppose plus q and minus q, and separated by a distance 2l. So, the dipole moment is P equals to 2ql. The electric field due to a dipole varies depending on the location where we are measuring it. We will consider two important cases. First, along the axis of the dipole, and second one is along the perpendicular bisector. The electric field due to a dipole varies depending on the location where we are measuring it. We will consider first case. This is the electric field along the axis of the dipole. For a point on the axis of the dipole, electric field is directed along the line connecting the charges and the point. The magnitude of the electric field at a distance from the center of the dipole is given by the equation E equals to 1 by 4 pi epsilon naught into 2 p by r cube. What is P? P is the dipole moment and P equals to 2ql. What is epsilon naught? Epsilon naught is the permittivity of the free space, and you know that r is the distance from the center of the dipole to the point where the field is being calculated. The factor 2p by r cube indicates that the electric field strength decreases with the cube of the distance from the dipole. The field direction is along the dipole moment vector, P meaning it points away from the positive charge and towards the negative charge. And the second one is electric field on the perpendicular bisector. For a point on the equatorial line of the dipole, the electric field is directed perpendicular to the dipole moment. The magnitude of the electric field at a distance r from the center of the dipole on the equatorial plane is E equals to 1 by 4 pi epsilon naught p by r cube. Here the field strength is also inversely proportional to the cube of the distance from the dipole. The direction of the electric field at any point on the equatorial line is perpendicular to the axis of the dipole and points from the positive charge towards the negative charge. In summary, the electric field due to a short dipole decreases rapidly with distance. This rapid decreases highlights the dipole localized effect. Next topic is our electric force. When an electric dipole which consists two equal and opposite charges and separated by a distance is placed in a uniform electric field, each charges experience a force due to the field. For a dipole with charges plus q and minus q and separated by a distance 2l placed in a uniform electric field, the positive charge plus q experience a force F1 and negative charge minus q experience a force F2, F1 equals to QE and F2 equals to minus QE. So, these forces are equal in magnitude, but opposite in direction. The net force on the dipole is 0. However, the forces act at different points on the dipole, creating a torque. Now, let us discuss torque. What is torque? Even though the net force on the dipole is 0, the dipole experience a torque because the forces act on the different points. This torque tends to rotate the dipole so that its dipole moment align with the electric field. And we know that torque equals to P into E. P is the dipole moment, E is the electric field, and we know that P equals to 2QL, and the magnitude of the torque can be represented by tau equals to Pe sin theta. Here theta is the angle between the dipole moment and electric field. So, electric dipole in a uniform electric field experience no net force, but does experience a torque that tries to align the dipole with the field. These fundamental concepts help us understand many physical and technological processes. Our last topic is equipotential surface. What is equipotential surface? It is a 3D, three-dimensional surface on which every point has the same electrical potential. This means that if a test charge moves anywhere on this surface, the electric potential energy remains constant and no work is done by or against the electric field. For example, if you imagine the surface of a lake as an equipotential surface, the water level is the same everywhere on this surface. Similarly, in an electric field, an equipotential surface represents a level where the potential is uniform. Equipotential surfaces are always perpendicular to electric field lines. This is because the electric field represents the direction of the greatest rate of decreases of potential. Therefore, moving along an equipotential surface where potential does not change, it must be perpendicular to the direction of the electric field. The spacing between equipotential surfaces indicate the strength of the electric field. Where the surfaces are closer together, the electric field is stronger, and where they are further apart, the electric field is weaker. Here diagram shows the point charges. Here the point charges is spherical. Why? This is because electric potential at any point around a point charge depends only on the distance from the charge. The equipotential surfaces are concentric sphere centered around the point charges. Suppose you imagine dropping a stone into a still pond. The ripples that move outward are like the spherical equipotential surface around a point charge. What is the property of equipotential surfaces? Equipotential surfaces are always perpendicular to the electric field line. This means that any point on an equipotential surface, the electric field is directed normal to the surface. When a charged particle moves along an equipotential surface, no work is done by the electric field because the electric potential differences along the surface is 0. At last, we discuss electrostatics application in technology, nature and industries. Let us start with something relatable. Imagine you are at a party and someone take a photo of you using an instant camera. Within minute, you have a physical photograph in your hand. Did you know that this process involves electrostatics? Similarly, when you print a document at home or in college, electrostatics helps transfer the toner to paper to create the printout. So, how it all works? First, photocopier. What is photocopier? Photocopier utilized electrostatic charges to create a duplicate of an image or document. Here we explain step by step. First of all, charging. A photoconductive drum or belt inside the copier is uniformly charged within a positive charge using a charger roller. The drum is coated with photoconductive material that becomes conductivity when exposed to light. After that, the original document is illuminated and the reflected light is projected on the charged drum. The area of the drum exposed to the light become conductive and lose their charge, while the dark area remain positively charged. Then developing process. Developing process start means negatively charged toner particles are then attracted to the positive charge area on the drum, which correspond to the image or text. The toner sticks to this area, forming a visible image on the drum. Then the process of transferring. A sheet of paper is passed through the copier and is given a stronger positive charge than the drum. The toner image on the drum is then transferred onto the paper due to the electrostatic attraction. Next is fusing. The paper with the toner image passes through heated roller which melt and bond the toner to the paper and creating a permanent image. Cleaning. The drum is cleaned to remove any remaining toner and is recharged to be ready for the next copy. Similarly, laser printers operate on a similar principle, but with some few differences. So, the application of electrostatics in photocopier, laser printer. The photocopier and laser printer is a remarkable example of how fundamental principles of physics are used in technology. These devices have become essential tools in modern life, enabling efficient and high quality reproduction of documents. We will discuss the application of electrostatics in electrostatic precipitators, an essential technology for pollution control in industries. Electrostatic precipitators are devices used to remove fine particulate matter from exhaust gases in industrial process, ensuring cleaner emissions and better air quality. Electrostatic precipitators are used in several industries: power plant, cement industry, steel mills. Last, we are going to explore the role of capacitor in electrostatics. Capacitors are fundamental components used in various electronic devices, ranging from simple gadgets to complex gadgets. They have a wide application due to their ability to store and release electrical energy. The fundamental principle of a capacitor is its ability to store and release energy. When a voltage is applied, the capacitor charges up, storing energy in electric field between the plates. When the circuit required energy, the capacitor can discharge and releasing the stored energy back into the circuit. At the last, now summarizing the today's lecture of electrostatics is here. We understanding how charge interact, the forces they exert on each other and the fields they create. Key concepts include electric charge, electric potential, electric field. Charges can be positive or negative, and like charges repel while opposite charges attract. The electric field is a vector field representing the force experienced by a unit positive charge in the presence of other charges. Electric potential describe the work needed to move a charge in an electric field. Electrostatic is fundamental to many technologies including capacitor, photocopier and electrostatic precipitators. As we finish up, remember that electric fields and potentials are all around us, from the gadgets we use daily to the forces that power our world. Keep exploring these fascinating concepts and you might discover something amazing. See you next time and keep your curiosity alive. Thank you.